If you liked induction, you're going to love this. Today, we are going to make induction stronger. You remember this guy. Well, now it's time for this guy. Let's do a quick review of the principle of induction. We are given a propositional function over the natural numbers. We know that P of 1 is true, the base case, and we know that P of k implies P of k plus 1 for all k's in the naturals, the induction step. Then P of n is true for all n in the naturals. I'm showing the statement from earlier lectures on this. This is what we did before. Okay, now for strong induction. Let P be a propositional function on the natural integers. Let's say we know that P of 1 is true, again, the base case, and we know that for any k in the natural numbers, we know that P of 1 and P of 2 and P of 3 and so on up to and including P of k implies P of k plus 1, then P of n is true for all natural numbers n. Note what is different here. In strong induction, we can assume that the proposition is true for all arguments less than or equal to k, not just k itself, and then prove P of k plus 1. And now it makes sense that there will be cases where we can use strong induction more effectively because we are allowed to assume more in the strong induction step. Quick note, sometimes in the context of strong induction, people refer to the simpler induction proof as weak induction. I'm not a fan of this at all because the induction we used up till now is anything but weak. So when necessary, I'll refer to what we did before as vanilla induction and what we are doing now as strong induction. Okay, so how do we prove the theorem of strong induction? Before we do that, let's first write down a lemma in predicate logic. The statement A implies B is equivalent to the statement A implies A and B. To prove this, we're going to just write out the truth tables and see that they are equivalent. Okay, so now how do we prove strong induction? Let us rewrite the theorem that we're trying to prove here. It turns out that we can do it without much work as long as we have one clever definition. Let me explain. Let P be any propositional function on the natural numbers n. Now define Q to be a different propositional function on n defined as follows. Q of n is P of 1 and P of 2 and P of 3 and ... P of n minus 1 and P of n. More explicitly, Q of n is true if and only if P of k is true for all k from 1 to n. Now let's apply vanilla induction to the proposition Q. Note that P of 1 is the same as Q of 1, and so by assumption Q of 1 is true. Now assume that Q of k is true. By the assumptions of the theorem, Q of k implies P of k plus 1. Using the lemma from earlier, Q of k implies Q of k and P of k plus 1. And note that Q of k and P of k plus 1 is exactly Q of k plus 1. Therefore, we have shown that Q of k implies Q of k plus 1. We can now apply vanilla induction to Q, giving us that Q of n is true for all natural numbers n. But of course, Q of n implies P of n, and therefore P of n is true for all natural n. And we are done. QED. Okay, now let's use strong induction. Let us first define a recursive formula for what are known as the Fibonacci numbers. We'll talk a lot more about what these Fibonacci numbers are later on, but here's a definition. Let us define the sequence Fn by f1 is 1, f2 is 1, and for all n greater than 2, fn is fn minus 1 plus fn minus 2. Basically, each term is the sum of the previous two terms. Let us write out several terms of the sequence. It starts 1, 1 by definition, then 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, 8 is 3 plus 5, 13 is 5 plus 8, and so on. Here's a side note about the Fibonacci numbers. You may recall earlier that these numbers showed up on an earlier homework assignment involving the Euclidean algorithm. It turns out that the Fibonacci numbers have many interesting and delightful properties, but one of them is that they are the worst case scenario for the Euclidean algorithm, interestingly enough. Anyway, back to the Fibonacci numbers, and we see when we write this sequence out that the Fibonacci numbers grow, but we're going to show that they don't grow too fast. Specifically, we will prove the theorem that the nth Fibonacci number, f sub n, is less than 2 to the n. Okay, let's rewrite the theorem. F sub n is less than 2 to the n. We will proceed by strong induction on the proposition P of n is that f sub n is less than 2 to the n. Let us first check two base cases. N equals 1, so notice that f1 is 1, which is less than 2 to the 1 because that's 2. For n equals 2, f2 is again 1, which is less than 2 to the 2, which is 4. Okay, so now let us fix k bigger than 2. Assume that p of 1, p of 2, all the way up to p of k is true. Then we have fk plus 1 is fk plus fk minus 1 by definition, which is less than 2 to the k plus 2 to the k minus 1 by the strong induction hypothesis, which is less than 2 to the k plus 2 to the k, which is 2 times 2 to the k, which is 2 to the k plus 1. And we are done. One note here. We had two base cases because of the form of the recursion. Since by definition each term depends on the previous two terms, we really can't start the strong induction step until k equals 3 because the formula only holds for k greater than or equal to 3. So we needed to do k equals 1 and 2 for the base cases. We can use the same idea to prove a nice generalization of this result. Choose a and b to be any numbers greater than or equal to 1. Now let us define a sequence g sub n. So g of 1 is 1, g of 2 is 1, and g of n is a times g of n minus 1 plus b times g of n minus 2. Then the theorem says g sub n is less than a plus b raised to the nth power. Note how this is a generalization of the Fibonacci sequence and a generalization of our previous theorem, because Fibonacci is just this same sequence with a equals b equals 1, and then the theorem would tell us it's less than 1 plus 1, which is 2 to the n, which is what we get. So as a concrete example, let's pick a equals 2 and b equals 3, and then the recursion is exactly gn is 2 times gn minus 1 plus 3 times gn minus 2. Basically, each term is you look back 1, multiply it by 2, look back 2 and multiply it by 3, and then add those together. Let's write out some terms of this sequence. And we get 1 and 1 by definition. Note that 5 is 2 times 1 plus 3 times 1. 13 is 2 times 5 plus 3 times 1. 41 is 2 times 13 plus 3 times 5, etc. We can see by eye that this looks like it grows faster than Fibonacci, but according to our theorem, it cannot grow faster than 5 to the n. Let's prove that theorem. First, recall by definition that a and b are both larger than 1, so a plus b is larger than 2. Now let's check n equals 1. So g1 is 1, and a plus b is bigger than 1, so p of 1 is true. G of 2 is 1, and a plus b squared is greater than or equal to 4, which is certainly greater than 1, so p of 2 is true. Now fix k and assume that the theorem holds for all numbers up to and including k. Then g of k plus 1 is a times gk plus b times gk minus 1 by definition, which is less by the induction hypothesis than a times a plus b to the k plus b times a plus b to the k minus 1, which is less than a times a plus b to the k plus b times a plus b to the k, which after factoring is exactly a plus b to the k plus 1. And we are done. Okay, in each of the previous two examples, we wrote a k plus 1 statement in terms of k and k minus 1, which was natural given the definition that we were working with. Now let's do an example that shows the full power of strong induction. First, a reminder. We say that any natural number greater than or equal to 2 is prime if the only way to factor it is 1 times itself. A number that is not prime is called composite, and we can see from the definition that if n is composite, then n can be written as n equals a times b, where a and b are both strictly larger than 1, or alternatively, a and b are both strictly less than n. Now we can prove the following theorem, which is 1/2 of what is called the fundamental theorem of arithmetic. Every natural number greater than or equal to 2 can be written as a product of primes. Note here that if a number p is prime, then we are going to write this as just p, which is a product with just one term. Okay, let's prove the theorem. First, we do the base case n equals 2. Since 2 is prime, it is written as a length 1 product of primes. So we're done. Now fix k greater than 2 and assume that the conclusion of the theorem is true for all numbers up to and including k. Now consider k plus 1. There are two cases. Either k plus 1 is prime or it is composite. If k plus 1 is prime, it is a product of primes, a product of length 1, and we're done. If k plus 1 is composite, then k plus 1 equals a times b, where a and b are both strictly less than k plus 1. Therefore, by the induction hypothesis, both a and b can be written as a product of primes, and by concatenating these two products, we have now written n plus 1 as a product of primes. And we are done. I said before that this was 1/2 of the fundamental theorem of arithmetic, and it's the existence half. One can also show, although we don't do that today, that when you write down this product, it is unique up to reordering, and that's sort of the other half. Let us prove one last theorem using strong induction, and here it is. Every natural number can be written as a sum of distinct powers of 2. That is to say, any natural n can be written as n equals 2 to the r1 plus 2 to the r2 plus ... plus 2 to the rq, where all of the ri's are distinct. In fact, we can always reorder these and use the convention that the ri's are a strictly decreasing sequence. So r1 is greater than r2, greater than r3, and so forth. Note that what this is really saying is that every natural number has a binary expansion. We simply put a 1 wherever a particular power of 2 appears, and a 0 where it doesn't. Now let us prove the theorem. First, we check on the base case n equals 1. Well, 1 equals 2 to the 0, and so we're done. Now fix k, and assume that the conclusion holds for all natural numbers up to and including k. Now consider the integer k plus 1. Let L be the largest integer so that 2 to the L is less than or equal to k plus 1. If k plus 1 equals 2 to the L exactly, then we are done. So let's assume that k plus 1 is greater than 2 to the L. Now define m equals k plus 1 minus 2 to the L, and since 2 to the L is positive, this means m is less than or equal to k, and this means that m can be written as a sum of distinct powers of 2. So m is 2 to the r1 plus 2 to the r2 plus ... 2 to the rq, and therefore k plus 1 is 2 to the L plus 2 to the r1 plus 2 to the r2 plus ... 2 to the rq. Now notice we're not quite done, because it's possible that these powers of 2 are not distinct. For example, it's possible that L is the same as one of the rj's. We will show that this cannot happen using proof by contradiction. So let's assume that L equals rj for some j. Then this means that m is greater than or equal to 2 to the L, which means that k plus 1, which equals m plus 2L, is greater than or equal to 2 to the L plus 1. But this is a contradiction because L was chosen to be maximal. Therefore, L is distinct from all of the RJs, and we've proved the theorem. Okay, that's good. I'll stop there.